have an example. We have a house here. The inside of the house is supposedly 80 Celsius. Well, that's really, really hot. The outside of the house is 25 Celsius. And this is one wall of the house. So this problem is not meant to be exactly how the typical homes are, but just give you an example of how to add different insulators in series and parallel, right? And then relate them to a typical question related to a house or any other kind of question, right? So now you have here a drywall, a layer of drywall that's 2 centimeters thick, and then fiberglass 7 centimeters thick, and then another drywall on the bottom that is 9 centimeters thick. And then we have the insulation factor of drywall for a ½ inch is 0.45 feet squared Fahrenheit hours over British thermal unit. And then the insulation of fiberglass for 3.5 inch fiberglass is 10.9 of the same unit. And then in the previous example, I talked about this in greater length in the theory section. And then towards the end of the video, I showed you that 10.9 feet squared Fahrenheit hours over British thermal units is also equivalent to 6.22 meters squared Celsius over watts. So the first thing let us calculate is the total insulation factor of this wall, the total insulation factor. So which ones of these are in series, which of them are in parallel, right? So the heat is going to be flowing here from the inside to the outside, like this, right? So the total power radiated through the top portion, right, is going to be the same because these two are in series, right? So these two are in series. So we can call the top one P1, and then the bottom one is P2, right? The power radiated through the bottom. So the top two are in series, and we have to calculate their total insulation first. Then the combination of those two, which are in series, is then in parallel with the drywall, right? So then you do the series first, then you would do the parallel. If the wall was like this, let's say you had drywall like this, okay? And then you had the material here, fiberglass, and you had over here, you had drywall. So then these two would be in parallel, and you have to do the parallel first. You have to do the combined insulation factor of the fiberglass with the drywall. You have to do the parallel first, and then you would do the combination of those two is in series with the outer drywall. Then you would do series. So this one is parallel first. If you are having a hard time visualizing this, then relate this to electrical circuits. If you have a battery, then you have a resistor, and then you have another resistor, and then another resistor, R1, R2, okay? Right? So then what is this going to be? Here you have to do the series first. These two, the current flows through them, the same current flows through them, right? So that's like this one. You have to do series first, right? And then you have to do parallel. So you might be thinking, well, these two resistors look like this. How do you know the difference? Well, you can visualize this way too. So it's not so much the orientation of the picture that determines what it is, but more what is going on. In this case, the current is going to come, split into two. This and this will have the same current. This and this will have the same power flowing through them, right? So then you have to do the combination of these, which are in series. You have to do R1 plus R2 is equal to R prime, right? Then you have to do that with the R3, parallel. So then you have to say 1 over R prime plus 1 over R3 is 1 over R total, okay? So this one is this one. So then what would this one be? Okay. So these two are in parallel, right? So the current comes like this, splits into two. These two have the same voltage drop across them, right? So then these two here, from here to here, have the same temperature drop. From here to here, from here to here is the same temperature drop. This one is the same voltage drop, right? So you have to do the parallel first, and then you can say the combination of that is in series with that. So you can say 1 over R prime is equal to 1 over R1 plus 1 over R2. So find out what R prime is, and then R prime will be in series with R3. So you can say R prime plus R3 is equal to R total. Same thing with here. These two are in parallel, so you combine their insulation factors in parallel, then you combine it with that in series, okay? So now let's get back to the example that we have. So these two here are in series we said, so then we say R prime is equal to R1 plus R2. So remember in the theory section, I proved to you that the insulation factor in series adds up exactly like resistors in series, right? So then what is this one here? The insulation factor of the drywall is the 0.45. Okay, but that is for half an inch. This one is 2 centimeters, right? So this one is for a half an inch. Then you say, you multiply that by 2 centimeters, and then you multiply that by the conversion. You say 2.54 centimeters is 1 inch. So the inch and inch cancel, centimeter cancel, and then you can calculate what the R1 value is, okay? And then you add to that the R2 of the fiberglass. So then you say here 10.9 divided by, that one is for 3.5 inches. And then you again multiply that by the thickness of the fiberglass, 7 centimeters. And then you multiply that by the conversion, 2.54 centimeters, 1 inch, okay? And then when you do that, you're gonna get this. R prime, the R1 is gonna come out to be equal to 0.70866. 0.70866. That is still in the British unit system because we haven't changed the units of the foot squared, hours divided by BTUs, right? The only thing we've done is to correct for the actual thickness of the material. So then you add to that this number, R2, and then R2 is the insulation factor of the fiberglass, and that one comes out to be 8.5826. Then you're gonna get, when you do that, 9.291. Then it's foot squared Fahrenheit times hours over BTU. Okay? Then you're going to say that resistance is in parallel with the drywall, right? So how do resistances add up in parallel? Well, for that we need the surface area, right? So imagine the house is like this. Like this. Right? So 2.5 from here all the way down to this layer, and then 1.5 from this layer to the ground. And then the 10 meters is the dimension out of the board or into the board, right? So how do insulators add up in parallel? So I'm going to rewrite what this picture looks like now. 1.5 meters, right? So then I'm going to say A prime over R prime plus A3 over R3 is equal to A total over R total. So these are how insulation factors add up in parallel. So A prime is going to be 2.5 times 10, right? This dimension was 10. That way. Well, what is R3? R3, this one is, since it's drywall, but we just have to correct for the 9 centimeters, right? The thickness. So let's do that. R3 is going to be, it's the insulation factor of drywall. So it's 0.45 over half an inch. Then we multiply that by 9 centimeters, because that's the thickness of the drywall here. Cancel, right? When you calculate that, you get 3.1889, and then that's going to be the R3, okay? And then that number goes over here. 3.1889. And now we can calculate this plus this is equal to 40 over that. You can calculate the R total. When we do that, R total comes out to be equal to 5.409. 5.409, and that's again in the same units, feet squared, Fahrenheit, hours over British thermal units. Okay, so that's the total insulation factor of the whole wall. This is how you would do any kind of wall. It could be 3 in series, it could be couple in parallel and another one in series. You would do whichever one is in series first or whichever one is in parallel, then you would combine them just like electrical circuits, right? So now we can convert that to the metric unit system, right? Right? Okay, so now let's calculate the total power flowing through the wall, the total power lost, okay, through the wall. So that could be part A of the problem, finding the total insulation factor of the wall, okay? So then you can say P total is equal to what? K total, A total, over L total, delta T, right? So this, I'm using the equation for the conductivity, the power loss due to conductivity, right? But then we're not working in heat conductivity here, we're working with the insulation factor, right? So I can bring the K total down here. P total is equal to A total, and then you write this as L total over K total, delta T. And then so I kind of can rewrite this power equation in a different way. This is going to be A total over R total, delta T. This is the total surface area divided by the total insulation factor times the difference of the temperatures of the inside and the outside, right? So then the P total is going to be, so the units, meter squared cancels, Celsius cancel, and then the answer comes out nicely in units of watts, okay? So then we can calculate that. And then when we do that, we get 712.8 watts. Okay, that's a lot of power loss, right? So then, with the techniques that we learned from the previous example, we could also calculate how many minutes it will take the inside of the house to reach down to 26 Celsius, right? It'll be an ln function again. So then we can compute that and we'll get a number and we'll say, oh, okay, that's how long it takes for the house to reach 26 Celsius, right? So I'm not going to do that here because it'll be the exact same as what we did in the previous example, okay? The other thing we can do now is to separate. Let's say if the problem wants us to find the power loss through the bottom drywall, okay? The power loss through the top, the top two, what is that? Okay, so separate them out. And then what was the R3? The R3 for the bottom was equal to 3.1889. 3.1889. But that one was in the units of the feet squared hours Fahrenheit over British thermal unit, right? Then I can convert that. I can say 10.9, 6.22. When you do that, you are going to get 453.4 watts. You see, the total power loss is 712, but 453.4 watts are through the bottom. Well, you see, that kind of makes sense because the bottom is dominating. Even though the bottom is thick, it's 9 centimeters, and even though its surface area is smaller, you would think if its surface area is smaller, right, that it should have less power loss. But the problem is that it's complete drywall, and drywall's insulation factor is very low. So most of the power is being lost through the bottom, you see. That's what happens when you have a house. If you have certain areas that aren't well insulated, you're going to have most of the power loss through those portions, right? So 453.4 watts are lost through the bottom, and then the top we can just do subtraction. Okay, 712.8 minus 453.4. That's going to give you 259.4. So the top, which we call P1, is equal to 259.4 watts. Okay? So now I can go one more step. I now have the power loss through the bottom. I have the power loss through the top. I can find out what the temperature is at this junction. In other words, between the drywall and the fiberglass. What's the temperature there? The temperature here. How do we do that? 59.4 watts. The area is going to be 2.5 times 10, so it's going to be 25. And then the R of the drywall, well, when we did that, remember we got 0.70866. 0.70866. That was correcting for its thickness also, right? But then we do the conversion again. 10.9 is equal to 6.22, right? And then delta T. But we don't know what delta T is, right? We don't know the difference of temperature from the outside to the right side of the drywall. So this will help us calculate the delta T. Okay? So when you do that, the delta T comes out to be equal to 4.2 Celsius. 4.2 Celsius. Okay? What does that mean? Well, this side of the outside of the house is 25. That means this side is 4.2 Celsius hotter, right? So 25 plus 4.2, 29.2 Celsius. Let's see if our answer is right. Let's apply the same technique just across the fiberglass. Let's see what we get. Okay? It's gonna be what? When we calculate that, we get 50.8. 50.8 Celsius. Well, what does that mean? From here to here is 50.8. Well, we already know right here the temperature is 29.2, right? 29.2 plus 50.8, right, is going to be what? 29.2 plus 50.8, well, that's going to show you what the inside temperature is, right? So when you do that, you get 80 Celsius. Okay, so it works out. So with this technique, I now have a technique of calculating the total insulation factor of any wall, depending on what the wall looks like. I can calculate how many minutes the house will take to go down to the same temperature as the outside temperature, or close to it. I can calculate how much power is flowing through any area of the wall, right? And I can also calculate the temperature of any junction inside of the wall, right? And any junction between two insulators, right? I can also calculate the temperature any random place. Any random location along the fiberglass, any random location along the drywall. So when you apply this to an actual house, of course, you now have to worry about the roof, right? Then you have to worry about the other side of the roof, the wall, and then also the ground too, the conduction through the ground to the floors, right? So when you do this, you get an actual applicable real life problem, okay? So now you know how to handle these kind of cases, okay? Thank you very much.